Good morning, ladies and gentlemen. Welcome to a short presentation on autonomous vessels, a class perspective. We are seeing an increasing trend to automate various processes in various sectors. Be it finance, that we are able to make a transaction using our Google Pay, or we are able to drive past your toll gates with RFID installed on our cars, or health informatics. Automation has made its roots in our daily life, apart from the industries also. The key technologies which have propelled the trend, I would put it up as the three main areas. One is information technology, digitalisation, and artificial intelligence. When we talk about information technology, it is not only the computer processing speed, but also the networking, the speed of networking, the advancements made in the network technology through which we're able to transfer without much of packet losses, and of course the bandwidth. Nowadays, we are able to convert any information into real time. Maybe it is a movement of the fingers, visualizations, sound, engine parameters. We are able to convert all the information digitally and analyze them. So digitalization has one of the main technology which has propelled this advanced automation. Way back in earlier 60s and 70s, we were using COBOL, Fortran, basics to make a simple programs, and we have come a long way where now we are able to mimic the human intelligence with using advanced neural networks, what we now call as a artificial intelligence. These are technologies which is just talked, maybe that networking, RFID, robotics, IoTs. These are all technologies, and cybersecurity like as a backbone which is making the things happen, which is actually sustaining these technologies so that things are transmitted safely and efficiently. When it comes to autonomous vehicles and autonomy, the car industry or automobile industry is little bit far advanced compared to the areas. I'm leaving the spacecraft because which is a different political altogether. So there are 5 levels of defense in this car industry. The defined by Society of Automotive Engineers. The level 0 is where the driver performs all the operations. Driver level 1, the cars are a little bit intelligent so that they can keep a safe distance. Driver is still in charge of the control. Level 2, SA2 they call it, is a partial automation. They can perform simple tasks. And as the levels goes up, the car takes over more and more of the driving and navigation part. And level 5 is the total autonomous. We take a parallel to our shipping industry, where autonomous vessels are just starting up. We have made a steady progress from the manned engine room to unmanned mission spaces, integrated navigation systems and bid systems, condition monitoring, route planning and performance optimizations, and of course the relation support system which have been just surfaced last 4 or 5 years back. Seeing the interest and work which is being taken care in the various industries happening in the various forums, I am more commence the work to look at how safe and secure and these vessels can be and how they can operate in environmentally friendly atmosphere. I am on defined 4 levels, degree 1, 2, 3, and 4. Level 1, where the ships with automatic process and decision support systems. We have seafarers on board. The control systems are there, they give decision support, but actual control is the seafarer. Level 2, the remote operated vehicles with seafarer on board. And level 3 is remote control without seafarers, and level 4 will fully autonomous. Before we go further, let us try to understand the philosophy of defining the levels, whether in the automobile sector or in the shipping sector. If you try to perceive a situation, any decision, it involves first of all gathering the information, understanding the information, and secondly, trying to understand the present situation and think what could go further from here, good or bad, and take a decision and finally implement the decision. So we perceive the situation and look at the situation where how it is going to happen, whether the current situation is conducive to me or is going detrimental to me. And finally, what is the future decision? All these decisions are the perceiving or the analysis is done by the human in most of the times. As these activities are delegated to the system, the level of autonomy increases. I collect the information, there's one part. We understand the information, make a situational awareness, and suppose we delegate that part, it is one level of autonomy. It makes a decision and gives two or three alternatives, one more level. It starts implementing the decision, then it's a higher level. So how the autonomy levels have been designed as we perceive the how a normal thinking of a human operator is transferred or delegated to the system. IACS on their part have established a task force wherein IRS as a member has been involved in close regulatory scoping exercise. The scoping exercise was done to identify whether those autonomous vehicles, level 1, 2, 3, or 4, to what extent they meet the present regulatory guidelines. The instruments, SOLAS instruments, MARPOL, all the instruments, how much they are meeting up, and what required to be done to change or modify or augment these instruments. Dedicated AX expert group was formed in the MAS, and IRS is a member of all the above two groups. We also represent AX in cyber system panel and the joint working group in cyber safety. Having understood how the autonomy is taking and how and the philosophy behind it, let us try to understand that vessel with advanced automation actually what are the key features are. They have obviously high degree of automation, and most of the cases they can have a remote control feature also. The automatic operation of all, it can be a part of the systems, maybe all the systems of the ships, like lookout, equipment health monitoring, ship maneuvering, machinery controls, cargo management, docking, undocking, and any other operations. One thing we all need to understand is autonomous need not be unmanned. That is a different access altogether. It is a question of making the systems more intelligent, more advanced. Whether we replace the human or not is a different part. Maybe it can reduce the human interaction. Because there are so many terminologies floating around for the autonomous vessels, we thought let us try to summarize them and keep it in a broad perspective. The autonomous maritime vessels can be broadly divided into two categories. One on surface vessels, and one which talks about the underwater. On the surface, we can have two broad categories: maritime autonomous surface ships, mass, quite a big compared to bigger ships, and unmanned surface vehicles, which we see normally which are being used by defense or by some survey launchers for survey purposes. Similarly, unmanned automatic underwater vehicles, we have two categories: ROVs and autonomous underwater vehicles, AUV. These are some of the key areas which are specific to an autonomous ship. Key focus areas, I would call that. How the ship communicates the shore. What should be the arrangement of the shore? Whether the shore will be controlling one ship or number of ships. How the human operator interacts at the shore center. What are the control centers? How they interact with the humans. Are we monitoring the safety and health systems on board? And since so much data is flowing in and out of the system, data integrity becomes a very, very important topic. And above all, the situational awareness and decision support system are the core technology which is actually making the autonomous system to go ahead. And cybersecurity, I would call it as a technology which is making these things sustain and take it forward. Of all the various areas you have seen, the three topics which are common to all the three and which require a special focus either from the shipyard, system integrator, or from the class perspective, are three: risk analysis, artificial intelligence, and cybersecurity. Risk analysis is the fundamental of all vessels, because especially when we are talking about autonomous vessels, risk analysis is a very, very important topic, and it needs to be done at different phases. It is not that we do risk analysis at one area. Right from the concept design phase, context specific risk, functional specific, system specific, cyber, and as per MSc circulars 1604, we talks about which has guidelines for trials. We need to also assess the risk associated with the trials. So these are the various risks in a nutshell which requires to be carried out in these autonomous vessels. We have got conventional tools for doing risk analysis. We all know FMEA, the fault tree analysis, and so forth. I've listed only one or two. But the new emerging method for doing risk analysis for complex systems, something like autonomous systems, is a system theoretic process analysis, STPA. Is an emerging tool which is already being used in cars and some other industries where systems are more complex, where there is a decision making involved. In a normal FMEA, we look at the failure of a system, whether the system has failed, a particular system fails, and what is the consequence. Whereas in STPA, apart from the failure, we also look at some of the underlying factors which may not be direct failures. For example, it can be human failure, human to infract. Suppose autonomous system prompts a human operator for a input to proceed further, and if it doesn't respond or responds late, then what happens? There could be a software bug, software system can be failure or it can be hanging. Inadequate control in the absence of component failure. So these are the four or various issues which are addressed in the STPA. Let us take an example. Suppose we are trying to control a rudder from a remote location. The moment a command is executed from the remote location, there is a time gap where it is processed, time it takes from the signal to travel from the remote control to ship, what we typically call the latency of the communication system, where it is processed in the ship, and finally, the time actuator has to respond, the time required for it to respond. If you combine all the times together, it may so happen in a particular instant, particular operational context, the combined time lag may be detrimental to ship safety. Control is executed, but it's too late to control. So STP analyzes such issues like too early, too late to control, and brings out the underlying factors and hidden factors which can really detriment to the ship's safety. The next part is AI, artificial intelligence. We say conventional softwares which follow a proper logic. In the sense, a simple logic, I would say rather. If yes, then what? If X, then Y. If the input load is increasing, yes, I have to increase my fuel input. Very simple. But when it comes to advanced systems, autonomous systems, the algorithms are different. Let me try to give an example. Suppose we are driving in a car with a very senior person with us, aged, when you say senior person, and we see two kids just running in front of the car. Now I have the two options: apply a sudden brake at the risk of hurting the co-passenger with me because the car may skid, or I go ahead hoping that I will clear the kids, or I take a small detour so that hoping that I will clear the children, or slow down again hoping that people will pass through. So these are the 3 or 4 alternatives. And what alternative the software designer has chosen while building his algorithm, and how it responds. And tomorrow it becomes more and more intelligent as it starts learning by itself, how it is going to respond. These are the very, very critical factors. So testing of AI systems is quite a complex job. And for that, we need 3 types of data: what we call development set, a training set, and a test set. The development set basically is an algorithm where the data is fed into the system and which has clear output and expected output. The system then automatically comes up with a mathematical formulas how to behave when this input comes. The next one is a development set. First was the training set, development set. So we are trying to check whether whatever algorithm already has been fed into system, how system has understood and how it is moving forward. So based on that, the model is further refined. Then finally, the test set. There is a fresh data, which is not a data which is used for either training or development, but it's totally different data, and we are trying to validate whether the system can behave predictably or as required to. Let us take a small example of data for collision avoidance and grounding. The initial training data could be called the rules of route, the chart information where the ship is flying, the images of radars, how to recognize the images, what are the possible scenarios, the possible objects, the sound signals, all this data into the fed in the system becomes, it starts learning. There's a small child, it starts learning the information as it grows up, it starts learning. Then the development data could be similar, but it should be a different data, the not same data, but it could be similar data. When we try to validate the whole system, then we can have a set as a radar image of very poor quality. Because there is a real life scenario. In real life scenario, you don't get exactly radar image which is very perfect. There could be condition, a situation where the image is foggy. Then maybe in the night time we are trying to move from image from night vision cameras. Then try to validate how the system is behaving under these circumstances. So with the help of three data, we are trying to train the data, develop it and refine it further, and finally test it with the different, more complex images, sound signals, and data to see whether the system is functioning accurately or not. One of the few points which is noticed, especially in the automobile and various industries in this advanced automation, there's a tendency of the operator to become a little bit casual when such automation is going on. Or the person, as we have seen, the automation levels 2, 3, and 4 in the car, or 1 and 2, 3 in the ships. The operator is supposed to respond immediately in case the system doesn't get over a particular problem. But if the operator is not trained and is not alert all the time, there have been a crucial and major fatalities. The training has become very crucial and shall be carried out for all new systems and technologies. It should be a specific role as per role, maybe on board or remote control centers. And since we are talking about a complex and highly automated systems, the simulator-based training is what is best and is recommended. And crew has to adapt themselves to the new method of working and understand the goals and objectives of this advanced automation when they are supposed to interfere or intervene and take control and take the reins. With so much distillation, so much of data that is flowing from the ship to shore, shore to ship, inside the ship, getting stored, getting processed later on. This protection of the data while it is transmitting from one pair to other area or when it is rest is crucial. So data protection techniques are required to protect the data in transit or data at rest. A small word of explanation here is due in the sense, compared to normal cyber risk management, is what we do in conventional ships. And here, there's a small change. Everything is same, except we don't talk much of policies here. Policies are important. It's not that they're not important. But when the ship is inching towards autonomous mode, then the physical and technical controls become more and more dominant and more important than the procedural. Procedures are important, but as the humans are removed, are going away from the system, distancing and delegating their powers to the system, then the technical controls become more important. So having a correct equipment, correct systems which can combat all this kind of cyber attacks is very crucial. We are at IRS, we had a vision for the management is a vision to support the industry when they're developing vessels with advanced autonomy. Our aim is to objective is to associate with them throughout the development phase and validating the systems and the design processes, provide input to the flag administrations on the models and the where they are being tests are carried out, review the test risk analysis as we discussed some time back in the area of operations, where it can be carried out, and of course, development of guidelines. We have taken up some few collaborative projects with the industry. Because of the forum, I may not be able to share the names of the industry, but I can share some of the work that has been going on, or at least has gone by. One was a lab-based project on network architecture for intelligent ships. And second, which is on go now, is in the technology demonstration of remote control vessels and autonomous vessels. When we say lab-based project, we had many objectives. Like one of the objective was to create a unified network in the ship so that all the data can flow to one location, have multiple VLANs in that, and test and segregate the VLANs with this separate data security features. And one which is quite relevant to the present context, what you were talking is how the ship and shore communication takes place, and what are the fallbacks, and how do we communicate the risk associated with it. I will just briefly touch upon that particular aspect. The objective of that particular test was to test and verify the automatic transfer of backup link, because redundancy is required. You have two links, one a primary link and a backup link to transfer the data from the ship to the shore. So in case there is a failure of the primary link, then automatically it has to go to the backup. And since we are talking about testing a technology demonstration, the backup link may or may not be as strong as powerful for the main link, which can also happen in the future. So we looked at alternatives which are different from the primary link. Suppose we are using a satellite system as the primary, there could be a microwave or some other system as a secondary link. And how do we optimize? Because the bandwidth of the secondary link may not be as strong as the primary link, because everything costs. So how do we optimize it? So that was one of the primary goals, to see how data can be transferred in case the primary link fails and it is received so that ship can still sail safely. Such prioritization, what we see is that improves the overall system response, reliability, and reduces the network congestion. So data priorities was the first thing, as I said, and data sequencing to avoid network congestion. Let me say to given a small example. In the ship, we have lots of data coming up. As customer, my friend was saying, it is 2 GB, 4 GB data is generated and stored. But for a ship to function safely and efficiently, there are certain critical data. And there are certain data which need to get monitored, maybe the condition of the equipment, the surroundings, any failures, non-critical failure, maybe AC, ventilation, so on. So it is very important to know which data is to be passed first, which has to come in the second. Is what is critical and what is less critical. I would not say non-critical or less critical. So we have called it critical, non-critical, and we also studied the latency effect. As we said in the earlier, latency has a lot of impact on the how the controls are transmitted and executed. The critical data which is required for the vessel movement and safety has a higher priority than the other types of data like images, video, etc., so that the network congestion is removed. So we have had the tool operational mode, the normal mode where the normal link is functioning, we're able to transmit all the data, and the backup mode where main link has failed. For the purpose of this particular project, for the lab-based project, we have identified 4 areas: non-critical, low critical, critical, and very critical. So we can club the bottom 2, critical, very critical, is a very important data, let us say. And the first 2, non-critical, lower critical, is the secondary data. So we had simulators in the lab, one generating the critical signals and one generating the non-critical signals. We had workstation, which represents the onboard workstation, and we had 2 communication links. and one more workstation which is represents a short station. So in the normal condition, all the data was made to pass to both the links, and we studied the effect of loss of one data and built algorithms and software so that in the critical data only gets passed when the main link fails, and it also sequences the data. That means sampling time is different. I think it calls for explanation here. Let us say like a radar. A radar moves at is 16 RPM. That is, or let us say 15 RPM. That means it takes a round in once in 4 seconds. If it looks at object, again comes back to object after 4 seconds. So it is perfectly fine if you update the position of the any object which is captured by radar maybe after 1 or 2 seconds compared to a engine parameter or oxygen engines parameters. So to save the existing bandwidth, you prioritize it. Don't try to rush up all the data together. Prioritize the data so which can be sent maybe a second or 1.5 seconds later can be sequenced. That means they're sampled at this particular time. So they're sequenced and made to pass to the communication. A simple graphical representation. We have got, let us say, 5 or 7 types of data. It includes basic computer data also. And we have a priority queue. You see the priority, the blue color dot, it has a highest priority of 7. And the next one, maybe the dark brown color has a priority of 6 and so on. The data from the ship then is prioritized, and when it sends out, you can see the blue one is first going out. Next, the red or the maroon followed by the yellow. That is, the priority 7 is first, 6 and 5. So when we take the example of our engine monitoring system, my monitoring controls and system data will be the first one to queue in. That would be followed by the other images like a STPA or radar images, so that the network is never congested and always optimized. And we also study the latency of the packets. That as we send the data, how much time it took to travel. Of course, because of the distance was less, the latency factors are good, but in the real time, it could be slightly more because of the distances as you move along from the, especially in the satellite system. We are talking about so much of technologies, technology software, cyber safety, and we discussed that it is very important for the cyber control systems to be technically stronger and to meet the requirement, because we cannot totally rely on the only procedural controls, because we are talking about a ship which is totally automated or advanced automated. So we have a guidelines for the certification of social systems, computer-based systems, guidelines on maritime cyber safety. We also have a guidelines on cyber safety for land-based installations, which will come in handy for the remote control centers. And we have a classification note which says, it talks about type of cyber security control system components. Here the control system components are designed to combat any kind of cyber attacks, and they are designed for 4 levels of controls. So you can have a component approved for level 1, level 2, level 3, level 4. The levels as they are, level 1 is very minimum level, which is designed to meet for casual incidents. Level 2, more serious, and level 3 is where someone purposefully is trying to hack a system. Level 4, there is a big group involved in trying to hack. That means these levels are basically the effort put by the hacker or how the incident may occur. Is it a casual incident, serious incident, or a dedicated cyber attack? So how the levels are defined, and our classification notes clearly brings out the requirements for each level. May the software or the hardware, a router or switches, PCs, we have that. So we'd like to conclude that what we need is a holistic approach for the risk analysis, right from the concept to design. The approach to AI testing has to be different. It can't be like a conventional software. Awareness and training and advanced systems play a critical role in safety. A simulation-based training is necessary. A life cycle approach from design to operations is required. And as since the data is flowing in and out everywhere, the data prioritization, the sequencing is very important so that you optimize your bandwidth and effective use of communication channels and both the main and backup channels. So that's the 4 areas, 4 or 5 areas we think we should be working on to realize the dream of autonomous systems. Thank you.
Thank you, Mr. Srinivas. Your presentation has just made us realize the sheer volume of processes, procedures that need to get into this environment, for us to enable to achieve their objective. Even for a class 1 level, the amount of steps that are needed are so detailed and prominent that, and as we progress, it gets even more complex. We have a number of questions. I will try and share as many as we have time for. The first question is about, could you please advise what is the environmental error in context? This was at the beginning of your session. You had spoken about compensation for environmental error. Are you?
Yes, I got it.
Yeah.
No, the systems are designed to operate in a particular environment. Especially either be hardware or software. When environment, I don't mean the physical environment of the heat, temperature, which we normally are associated, which anyway the systems are tuned to for that. It is designed in the environment in the sense the operator efficiency. What is the backup you have at the control centers? How the systems are functioning, how they fails, what are the possible fallbacks? So it is a holistic environment. It's not an environment of the, let us say, humidity or temperature, but it is an environment in which we are operating. Like we say, we are in the environment of intellectuals, environment of a terrorist. So that is the kind of environment. So systems, when we design them, it has to perceive that. And system once designed for one kind of environment may not actually work properly if you are trying to take it to some other environment. Suppose in a lab-based model or in the testing environment, everyone is trained, all the engineers are trained. So you know what is anticipated. But when you hand over the ship to the operator, then it's totally different. Then we have to ensure that the training, the fallback procedures are clearly understood and implemented so that things move as they're planned.
Correct. Thank you, sir. The next question is about component failure. The question is, how can we come to know, which I'm assuming is if there is a component failure, and if the vessel is in channel, if any failure takes place, how is it handled? So I'm assuming if the vessel is in a critical traffic area and there is a failure, how would these things situations be handled on an autonomous vessel?
There are two ways. One is if it's not only when autonomous, when a conventional ships, if you see, the trend is to avoid the failures. Knowing when the failure happens is quite simple because you lose the signal.
Yeah.
Suppose my control system has failed, I know that signal is lost. Okay, I have a redundancy switch to the second controller. The ship function is maintained, but it has failed. We come to know. Power supply failure, we come to know. But the challenge is in trying to identify whether it fails before it fails. That's where this predictive maintenance, condition maintenance, everything comes into picture. The predictive maintenance is where it steps in. So we try to capture all the basic parameter information from each controllers, motors, engines, like temperature, humidity, the vibrations, all the parameters which are give indication whether the equipment is going to fail or is likely to fail. So predictive maintenance plays a major role to address this part. The idea is to stop something from failing. After it fails, you have redundancy, you have a backup, you can stop the ship, all things can be done. But predictive maintenance is what plays a major role here.
Yes, absolutely. Makes sense. We prevent it rather than have to actually resolve it once the situation is created. It's a very interesting question, which is, I can see from a very practical aspect, how will autonomous vessels deal with PSC inspections? I mean, we're talking about the current regime of port state inspections that are there.
I know it's a tricky question to, interesting question to ask and tricky to answer. But point is, that's why the IMO has come with the scoping exercise. Now that's what they are trying to look at in the scoping exercise. What are the existing instruments what IMO has, and whether these autonomous vessels really they do comply, they don't comply. In fact, the scoping test exercise they found that level 1 is more or less fine, but 2, 3, and 4 needs a lot of improvement in the existing instruments.
Correct.
Maybe augmentation or change it is required. That's what the scoping exercise recently concluded has come out. I think it is still some time now. But what then the question may come, then why we are doing all these things?
Correct.
So point is, we are trying to make a technology demonstration, not only ARS elsewhere, it may be Consberg, Rolls-Royce, whoever it is. So that once the regulatory regimes and practice are in place, we have the technology.
Right.
That is the idea, because the technology takes a time to develop. It is not that it comes, and even the regulatory practice, the IMO or maybe local flag administration, they derive the contents only when your technology is in place and try to prove it. Because otherwise it becomes only a science fiction.
Thank you, sir. That concludes our time for the Q&A session. There are a couple more questions, and we will pass them on to you for your response down the line.